The objective of the experiment number 9 is to determine the torsional oscillations of a single rotor with viscous damping. So before performing the experiment related to viscous damping, let us see that what is the viscous damping. We know that in viscous damping, fluid medium such as oil or gas which resists vibration and causes energy to dissipate. And because of the linear behavior of the viscous damper, we give it importance from the other types of damping. In this experiment, the effects of introducing dashboards into a system undergoing torsional oscillations are investigated. The amount of damping in the system can be shown to be proportional to the area of contact of a dashboard piston with a viscous medium by using a conical flywheel, which may be raised and lowered into the oil by means of a fine adjusting screw. The corresponding equation of motion of damped angular vibration is written here. In this experiment, we are studying the damping torque per unit angular velocity and its behavior with the change in the area. The apparatus for this experiment, we used this apparatus. This is a conical flywheel, and this flywheel is immersed into the oil sump, and this is the dashboard. What we will do, we will fix a graph paper on this drum, and with the help of a pen, we will take the readings of oscillations. Then from this graph, we will determine the relation of C with the area. The apparatus for this experiment consists of a vertical shaft gripped at its upper end by a chuck bolted to a bracket K1 and its lower end by a similar chuck which is integral with a heavy flywheel K3. Flywheel K3 suspends over a transparent cylindrical container K4 containing damping oil. The oil container may be raised and lowered by means of a thumb nuts beneath, and in the process the area of contact between the oil in the container and the surface of the conical flywheel attached beneath the heavy rotor can be altered. In the process, the area of contact between the oil in the container and the surface of the conical flywheel attached beneath the heavy rotor can be altered. This effectively varies the damping force on the oscillating rotor. A recording of the torsional oscillation is produced by a vertically mounted chart drum which is mounted above the flywheel. Assembly K2 consists of a pen holder and pen which may be adjusted to contact the chart drum and which undergoes a controlled descent over the length of the drum by means of an oil dashboard clamped to the main frame. Various shaft diameters may be used, but due to the location and necessary fine adjustments of oil containers, the length is restricted to approximately 0.775 meters. The angular displacement of the flywheel may be assessed by reference to a graduated angular scale around the upper rim of the flywheel. A perspex bracket within each center line bolted to the frame acts as a zero datum for the angular displacement. The cylindrical container K4 should be filled with oil to within about 10 mm of the top and the thumb wheels beneath adjusted so that the oil surface is brought level with one of the graduations on the conical flywheel. Details of the graduations are given in this figure. So we have selected D as a 75 millimeters and the height is 37.5 millimeters. After selecting and fitting a suitable shaft, the length of the shaft between the two inside chuck faces should be noted, in addition to the shaft diameter. The The rate of descent of the pen in millimeter per second should be measured by timing the descent of the pen over a fixed length of paper by means of a stopwatch. The torsional oscillations of the system for any chosen damping area can then be recorded. The pen should be raised to the top of the chart drum and the rotor rotated through a suitable angle about 20 degrees and released. A trace of the oscillation can then be obtained by bringing the pen into the contact with the chart drum using the thumb nut on the support and allowing the pen to descend. A trace of the amplitude of oscillations will be recorded showing decay of the vibration due to the damping with respect to time versus the descent of the pen. A characteristic trace can then be obtained for each of the damping areas defined by the 7 graduations on the conical rotor. But we are doing for only for the one area which we have selected. The traces may be analyzed to determine the logarithmic decrement of the damping by measuring the amplitudes of successive oscillations. So here we measure the amplitude of two successive oscillations, which is y1 is equal to the 8 millimeter and y2 is equal to the 7 millimeters. The radius of the base of conical section which is immersed is equal to the 37.5 millimeter. It is equal to the 75 millimeter. Diameter is equal to 75 millimeter and radius is 75 divided by 2 and the radius is equal to the 37.5 millimeter. First of all, we will calculate the theoretical time. Then we will calculate the practical time. So theoretical time can be calculated from this formula. Here T is the periodic time in second and I is the moment of inertia in kilogram meter per square and L is the length of the shaft in meters and C is the modulus. This is the capital C. Remember, C is the modulus of rigidity and 8.276 into 10 raised power 10 Newton per meter square. Do not confuse this C with C, capital C of damping torque per unit angular velocity. J is the polar moment of inertia and it will be equal to the pi r power 4 upon 2. We know the diameter of the shaft, so we can calculate the polar moment of inertia for the shaft. Moment of inertia of a flywheel is given to us, which is equal to the 0.113 kilogram meter square. We can calculate J from this formula, and J is equal to the 9.99 into 10 raised power minus 12 meter power. So here we know the moment of inertia of the flywheel. We know the length of the shaft, and we know the modulus of rigidity, and we know the polar moment of inertia of the shaft. We can calculate the theoretical time period, which is equal to the 0.687 seconds. Theoretical time period is 0.687 seconds, and we need to find the actual time period from this graph. What information we get from this graph is the length of this graph is 115 millimeters, and from the stopwatch we measured the time period is equal to the 14.68 seconds. The amplitude of two successive wave is 8 and 7 millimeters and the pitch is 5 millimeters. So when we divide the y1 with the y2, we'll get the ratio of 1.143. After getting the log of 1.143, it will be equal to the 0.058. We can measure the rate of descent of this stylus from the graph. Rate of descent is equal to the length covered by the stylus and time. So it will be length is equal to the 115 millimeters and time is equal to the 14.68 seconds. So the rate of descent of stylus is equal to the length divided by the time it covered, which is equal to the 7.86 millimeter second. So for calculating actual time period, we need to know the pitch, which is equal to the 5 millimeters from the graph, and divided by the velocity, the rate of descent of the stylus, which is equal to the 7.86, and pitch divided by the velocity is equal to the actual time period, which is equal to the 6.636. Theoretical time period was 0.687 and actual time period is 0.636. So from these values we can find the value of A. which is equal to the 2 upon the periodic time multiplied by the logarithmic decrement. So A1 is equal to the 0.183 per second. So by knowing the value of A1, we can find the value of C, as A1 is equal to the C upon I. So C is equal to the A1 times I. We know the value of A1. So in order to find the value of C, we know that C is equal to the C upon I is equal to the A1, and we know the value of A1. So we know the value of I for this experiment is 0.113. So C is equal to the 2.6 kilogram meter per radian per second. Now if we know the value of C, then we can plot it against the area into mean radius and find its variation with increasing or decreasing the area. So the damping area is equal to the pi time radius times the length. So this length is the slant height of this cone. As we know the height and radius of the cone, so we can find the slant height for our case. So slant height can be calculated from this formula under root r square plus h square, where r is the radius and h is the height. So the slant height is equal to the 53 millimeters for this. For our case, we have selected the d is equal to the 75, so r will be also equal to the 37.5, and our height is 37.5. If we know the slant height, we can find the damping area. Damping area is equal to the 6244.73 millimeter square. So in our case, our mean diameter is 75. So the mean radius will be equal to the 37.5 millimeters. But if we will change the our area by adjusting this screw, then our mean radius and damped area will change. But for the particular case, we have a damp area times mean radius is equal to the 22,34,177.37 millimeter cube. So basically it is showing us the volume of this cone. Now we have all the values of these above parameters. We know the value of C, and we know the value of damp area times mean radius. So we can plot a graph between damping torque per unit angular velocity C and damping area times effective mean radius. So these values can be plotted here. C is plotted on the vertical axis, and on the horizontal axis damping area and the effective mean radius can be plotted. And from this graph we can see that from above we can conclude that the torsional escalation of a single rotor with viscous damping is determined for a particular damping area, which is equal to the 6243.73 millimeters square. You can change the value of area by adjusting our screw, and we are not going to do, but if we will do, then what will happen, then the greater the damping area, faster would be the decrement is the for torsional oscillation, as both of C and A into R means are linearly proportional. Damping coefficient and damping area are directly